Okay, so something slightly odd happens when you apply these transforms, because the transforms were constrained by the rules we gave. Right? The transforms were constrained by must preserve normal component in the case of the contravariant transform, must preserve tangent component in the case of the covariant transform. So that means that something slightly surprising happens if you ask yourself what actually happens to a vector under these transforms. Right? This is ever so slightly mind-bending. It's sufficiently mind-bending that I might get the drawing. Right. So imagine I've got my reference triangle. So I draw that one, and they've actually. So this is going to be. Right. And so Marie's very helpfully done an actual practical example where she has mapped this to another triangle which is the other way round and is somewhat bigger. And she's mapped it so that this is 1 and that's 1, this is 2 and that's 2, and this is 3 and that's 3. And then she's asked, so if I have a vector which is a tangent vector here, and a vector which is a normal vector here, and I map them through the contravariant, so this is the H div case with the contravariant Piola transform. If I transform these under the contravariant Piola transform, what happens to them? So remember, the contravariant Piola transform is the one that preserves the normal component of the transform. This means, bizarrely enough, that a tangent vector goes to a tangent vector. Because the normal component of this vector is 0. So under a contravariant Piola transform, the normal component of this vector must be 0. That's what the transform means. Conversely, this guy does not go to a normal vector. The transform of this guy, if you work out the maths, goes to something which looks like this. So what the hell happened there? Well, the answer is that, remember the promise that the contravariant Piola transform gave us. This thing is preserved up to the edge length. Right? So it doesn't say anything about, so this thing is not going to be the same length as this thing, and this thing's tangent component is not going to be the same length as that. And that doesn't matter. The reason that doesn't matter is because this thing has well-defined, so you sum these you sum these functions up and they give you a well-defined value in this triangle. You do the transform for the next triangle, you sum them up and they give you a well-defined value in that triangle. And they're not continuous because they're transformed in different ways. But that's fine because we didn't ever claim that the function was going to be continuous from one triangle to the other. What we claimed was the normal component of the function would be continuous. And the normal component of this function is preserved under the mapping up to the edge length. And the edge length is the same from both sides. So you get to keep exactly the amount of continuity that you needed. But it's still slightly weird, right? You are expected to think it's kind of odd that the transform which preserves normal components takes tangents to tangents but doesn't take normals to normals. Something which, having done that, is now the obvious result, happens if we take this off here and take this off here and now ask, okay, what if this was an H curl space? and we were transforming with the covariant Piola transform. So the covariant Piola transform makes the promise that it preserves the tangent component. So that means that when we transform this guy, it's going to turn into a normal. Won't be a normal of the same length because this transform doesn't make any promises about the normal component. So the normal length can change to anything. But if we start with a tangent component of 0, we have to end up with a tangent component of 0. Conversely, this thing ends up, well, I'll believe Marie when she says that it ends up over here. I assume that she's actually calculated it out. And so our tangent component here does not end up tangent. But its tangent component will be the same up to the rescaling of the edge length. And so exactly the same logic applies, right? So when I ask myself, what does this global function now look like? Well, the transform in this triangle is not the same as the transform in this triangle, so the functions are not going to be continuous. But the tangent component of the functions will be the same. So I get exactly what the promise was, which is the tangent component is continuous, and nothing was promised about the normal component. The normal component will in fact be discontinuous. So that's the graphical, physical intuition of what goes on when you use a Piola transform. And the same thing happens in 3 dimensions. I'm not going to, so even the paper doesn't write out the 3-dimensional case because the 3-dimensional case just gets horrifically messy, particularly once you start worrying about 3-dimensional tangents because you've got 2 of them. You have to keep worrying about what the relative orientations of each other are, and the whole thing turns into a horrific mess. But actually we don't need to care because all of the important principle is here. So it's still going to be the same in 3 dimensions. So in 3 dimensions, the contravariant Piola transform will still preserve the normal, and the covariant one will still preserve the tangents, and the same result therefore falls out. So that's why that works. If you and so if you follow that through to the practical implications of what's going on, when we actually implement, this tells us then the set of tools that we need. And so given any form that I'm given, and functions in any function space, and the form having any derivatives in it, we have a toolkit of change of coordinate operations. So we know how to transform the gradients, and that doesn't change for what basis function you're in. We know how to transform the all the different function spaces. So if the functions are in H1, if they're just normally continuous, then the transform is trivial. Function over here equals function over here, and we now know the rules for HDiv and HCo. If you get beyond that, you can get really clever about this, right? So it's one of the cases that someone actually raised as a question in a previous lecture, but we can now understand it happening, is what happens if I have the divergence of U in physical space, and I want, and U is in HDiv, so I'm allowed to take its divergence. And the answer is, so this thing becomes that. So I think in the way round that this paper is using, that's a minus t. It's the covariant transform. It's just a question of which way around you choose to define which covariant. And this guy, as we've just learnt, becomes J over det J U in local. and because of the dot product, they go out. So you actually just get the local divergence scaled by the size of the triangle. And if you integrate that over a triangle, of course, that's, this will even cancel out. So there's a slightly surprising effect that if you integrate the divergence of something in an HDF space over a triangle, it doesn't matter what the geometry of the triangle was. And one way you can understand that statement is by thinking about Gauss's theorem. Gauss's theorem basically says that you can integrate by parts and turn a divergence into the flux, and the degrees of freedom on this space were in fact the fluxes. And so in some sense the geometry was already taken into account in the space. So when you take the divergence, it just drops out. Those who are interested in the software we currently use, that cancellation does not currently work. Be a very nice paper for someone if they can make that work. It's a quite complicated symbolic algebra trick to make that one fall out. But we are doing some work on an exterior calculus language in which that just falls out because it's much easier to do an exterior calculus. So we have about 20 minutes left, and I think I've said all I'm going to say about Piola transforms. So I thought that I would just chuck up on the board a little bit about what's going on in mixed spaces and why we have mixed spaces and what a mixed problem looks like. So I'm going to do the classical thing, which is I'm going to go back to our favorite problem that we started with right at the beginning of the course, and we're going to say minus the second derivative of our function is equal to some known function on the right hand side. And we're going to look at this in a slightly different way. So what we did previously was we formed the weak form of this and we integrated by parts and we got down to an equation that only had first derivatives in it. There's another way of only getting to first derivatives, and in fact to get to that, in order to avoid confusing the hell out of everybody in a minute, I'm going to relabel my function as being for p. So the reason I'm going to relabel it for p is because you can think of p as standing for pressure. So this is the Laplacian of pressure is equal to something we know. The reason we're going to do that is because we're going to bring in a variable which effectively is velocity. And in a lot of the literature for this, because it comes from elasticity, they use u as the primal variable, and then they use something else for the vector valued quantity. You have these horrifically, if you're a fluids person, horrifically confusing papers where there's u's all over the place and the u isn't the velocity. So let's be fluids for a while. So what we do in order to turn this into a first order system of first order equations, is the trick that you learned in your undergraduate ODEs class, which is we just make a variable substitution. And so what we do is we say that the gradient of p is going to be equal to a function u. In fact, we might, I think it's traditional to put the minus sign in this one. It doesn't matter which way you split it. So now I can make that substitution into here, and I get that the divergence of u is equal to f. So now that's a system of first order equations which is equivalent to my second order equation here. And so now we want to apply the finite element method. So in order to apply the finite element method, we need a weak form of this equation. So in order to have a weak form of this equation, we need to actually have an understanding of what it means to be a solution of this equation. And in order to solve this equation, you actually need two variables. You need p and u. And it's equivalent to that to just slam those two together and say, let's have a new function space. And the new function space has variables that have two meta components, two big components, a u part and a v part. So I can say, so let's assume that u is in some suitable function space vu, and p is in some, sorry, not equals, is in some suitable function space vp, and I now form what we call the mixed space. And so I say v is equal to vu vp. And so this is the space of functions u, p, such that u is in vu and p is in vp. And that's a perfectly good function space in the sense of being a vector space in this way that we've learned in this course. Right? So what has to be true? It has to be true that that I can add these things, which I can. So I add them just by adding the components. So the two functions I'm adding each has a u component and a p component, and the output has the sum of the u components and the sum of the p components. I also have to be able to multiply by a scalar, and that's easy. I can multiply this by a scalar, and I just multiply the u and the p parts by the same scalar. So that's perfectly well behaved. And we can then ask ourselves what the basis for this space looks like. And that answer is also rather simple. So if phi u is a basis for vu, and I guess I need an I in there, and if psi, actually that's a better idea, if phi I is a basis for vu and psi j is a basis for vp, then the space given by phi I 0 union the space given by 0 psi j is a basis for V. Right, so all that's saying is I can get any function in here. So any function in here is a sum of the basis for the u bit with p set to 0 plus a sum of the basis for the p bit with u set to 0. So that should look really familiar, because really that's just like the basis for a Cartesian product vector value basis function. So in many respects it works the same way. And so now what happens back up here is we want to write then a weak form by multiplying by a test function and integrating. So what we're looking for is find u p in V such that, and okay, so I'll leave that in a box on the board and let's write out the weak form. So the integral of v dot u minus v dot grad p dx equals 0, and the integral of q dot u minus actually we can write it like this to show what's left on my hand side, equals the integral of q f dx. So that looks, and this has got to be true for all v q in v.
Plus or equals.
Sorry? That's a plus, yeah. Yeah. That's right. My inability to do high school algebra is a severe impediment in my career as a applied mathematician. Right. So, what have we just done? So, what we've just done is we've actually, at each point, multiplied by the whole test function, because that's what you've actually got to do. Right? The weak form says we take our equation, we multiply by the whole test function. And the reason why this fell out to look like this is because really when I wrote u here, having said that u is in this space, this is really a shorthand notation for u0. And so if I take vq dot u0, this part of the dot product is going to go away. So that's just the same as v dot u. And similarly for the other half of the equation. So now, knowing what we've just learned about function spaces, we can ask ourselves whether what we've got here is suitable and appropriate. And the answer is, well, it's going to depend on which function spaces these guys live in. But there are some good answers. And one particular good answer that a lot of people around here care about at the moment is, let's go back to what we just said and say, right, so the important thing about u is we need to be able to take a divergence of it. And if that's true, then this equation, which is effectively the equation for p, is going to result in something which matches div u. And so in a hand-wavy sense that is vastly more precise if you do the calculus derivation, that tells you that you wanted your pressure to be in the discontinuous space. Okay, so far so good. So if we're going to put this in HDiv, that's a legal operation, right? There is a weak divergence in the HDiv space. That's why we call it HDiv. This one, on the other hand, is naught. Right? If we choose P to be in the discontinuous space, then there isn't a weak gradient. Right? Many, many weeks ago, we learnt that if you're just in L2, you don't have any continuity at all, then we don't really have a rigorous meaning for that. So actually, in order to get there, we needed to integrate that term by parts. If we integrated that term by parts, what we get, let's just lose this stuff over here, is, so now I've lost myself, so there's the problematic term, the grad P. So that doesn't change, minus div v p dx plus integral over the boundary of v dot n p Okay, that's the integration by parts formula in that circumstance. So now where are we? So if U is in HDiv, that means V is in HDiv, right? Because we're doing a straight Lurkin method, and we have the same function space here and here. So U and V have to be the same, and so that means we're allowed to take a divergence here. So now this becomes a completely above the board and legal set of equations. And for added bonus marks, you've actually acquired a mechanism for applying a Dirichlet condition on P there. And if you look at the way this equation works, because P and U are related by the gradient, that's actually also equivalent to a Neumann condition on U, if you care. So it's equivalent to a grad U dot N condition. So what's going to happen then when we assemble this system? So when we assemble this system, in order to get the left-hand side, we have the normal situation where we get a matrix, and the rows of the matrix correspond to the basis functions of the test space. That's the normal rule. So remember what the basis functions of the test space looked like. They were a set of functions which had a U component and nothing, and then a set of functions which had a P component and then nothing. So what we get here is a set of equations where we've got all the V parts, right? All the test functions, all the V parts of the test functions, and a set where we're testing with all the P part, all the Q parts, sorry. And correspondingly, so remember how we get this equation. We get this equation by every time we have one of these guys, either a U or a P, respectively a function in this space, in our equations, we replace that by the sum over the basis functions of the coefficients of those basis functions and the basis functions. So the columns of this matrix correspond to the basis functions of this space. And so the same thing happens. So you get a U here and a P here. So you get this block structure in your matrix. So in our case, if we look back here and we ask where do all these things end up, so the integral of V dot U ends up in this block, and that looks like a mass matrix in that block. And in this block, we get the integral of minus the integral of div V P plus the boundary integral of V dot N P, right? V test function, P trial function. In this block down here, we get the integral of Q div U, and in this block here, we get the integral QF. Sorry, I get 0. QF is a right-hand side term. So error there, there's no P in that term. Right. That block comes from a slightly counterintuitive result that the equation for P has no P in it. That's true for this equation as a whole. It's related to the null space of this equation, actually. So having written that, what we've effectively done is reduced the assembly of this equation to a problem we solved earlier. Right? So having done this complicated thing where we made a mixed space by ramming stuff together, we now consider the assembly of each of these matrices separately. There's no complicated mixed stuff going on. Each of these matrices is just a normal finite element matrix with a normal finite element test and trial functions that we understand. And it turns out that treating them that way has some advantages, because if you do that, then you can preserve these blocks when you build the matrix. You actually get a block matrix, and that opens up a beautiful world of block-based solvers, where you do share complements on this matrix, you can do different preconditions on different blocks, and so on. Having remembered that is an important step for me. And much of the software that we work with either does that now, Fidrate does that now, Phoenix is moving towards doing that. I even think in certain circumstances some of that happens in Fluidity as well. It happens in a much more manual way. Okay, we are just about out of time now, and I think that's probably all I had to say. And for those of you watching this on the web who haven't heard the announcement earlier, that's probably the last lecture in this course, so that's the end of it. Thank you very much.